All right, ladies and gentlemen, this is going to be review video 30 about how to draw multi-step potential energy diagrams. So, before, when we talked about single versus multi-step very briefly in our reaction rates video, I told you that you're never going to have to draw a multi-step potential energy diagram on the AP test, and that is still true. However, we're going to do it as practice in this class, and what you will have to do on the AP test is analyze them and understand them, and learning how to draw them helps you do that, so we're going to practice that skill anyway. So, single step ones, the ones that you see over here, you've seen those before. We know what the different pieces mean. We know that E sub R means the energy of reactants. We know that E sub P means the energy of products. We know the distance between where the reactants are and the top of this hill, or the activated complex, is the activation energy, which is the energy input required to make that reaction function. And we know that delta H means the change in enthalpy between the reactants and the products, completely separate from the activation energy. Multi-step reaction diagrams are the same. They just show each individual step of the reaction itself. So we still see the energy of reactants, we still see the energy of products, we still see an overall delta H value. But what is different is the hill in the middle, because now there's more than one of them. So step one is represented by our first hill, and that's going to have an activated complex for that step, which means that that particular step has its own unique activation energy, or the energy input required for that specific step. What that step also has right here is an overall delta H value for that step alone. All right, and that becomes very important when you're asked questions like, hey, is this particular step endothermic or is this particular step exothermic? Because you can look at this little bit right here, the intermediates of the multi-step reaction, and determine if the intermediates are higher or lower energy than the reactants were. So in this case, for this particular step right here, that is an endothermic step. And I know that because the intermediates are higher in energy than the reactants originally were. Now, for step two that I'm seeing over here, it has its own activation energy requirement. And we're seeing that that activation requirement for the second step is actually less than the first, meaning that that second step requires less energy than the first one did. We are also seeing that between here and the end, the products, they have lost energy over time, making this particular step exothermic, whereas the first one over here was an endothermic step. And we can just analyze that based on looking at the multi-step reaction graph. All right. One specific thing that I want to talk about is the step with the largest activation energy. So once again, looking at this graph, that's pretty easy to identify. We see that that distance is longer than this one is, meaning that step one has the largest activation energy value. What that tells you is that in a mechanism series, that first step is going to be what we call the slow step. And the slow step is the step that's always going to drive the speed of the reaction, because no matter how fast the rest of the reaction goes, the reaction as a whole cannot go faster than the slow step goes. So however fast the slow step is going, that's more or less going to match the speed of the entire reaction, because the faster steps tend to happen a lot faster than the slow steps will ever happen. All right? And once again, each step could be endothermic. And again, this first step with this first hill is an endothermic step. And we know that because our E sub R and our intermediate step, we've gained some energy. Or our steps could be exothermic. So this step right here is an exothermic step because we see that where we start for that step, we lose energy by the end. So that would be our exothermic step. The important thing to remember with endo and exo is that you're very rarely going to be shown a graph for mechanistic steps. Sometimes you will be and you get a nice graph to look at, which is great, but most of the time you're just going to get a delta H value. So that delta H value can tell you that information. If that delta H value is positive, and that step has like a positive 100 kilojoules per mole of enthalpy change, you know that step is endothermic. because positive means that we have absorbed energy. That's what this would look like on the graph. If that delta H value is negative, on the other hand, that means we've lost energy. And on a graph, this is what it would look like. All right, so we're going to practice real quick. We're going to sketch a potential energy diagram for the multi-step reaction below, and we're going to assume that we are starting, our E sub R starts at 60 kilojoules per mole. And once again, I want to reiterate, you're not going to have to do this on the AP test, but I am going to make you practice that skill so that you understand these diagrams really well. All right, so let's look at what we have. We have step 1, which is represented in green over here. We are told what's going on. So we see the reactants and products of that step. We are told that it's an equilibrium, and we are told that it is a fast step. The word fast is going to tell you that our E sub A for that particular step is low. All right. We are also told a delta H value for that step, and that delta H value is negative, which means that that particular step is exothermic overall. All right, so let's look at our blank graph and let's sketch out that particular step. Once again, I'm going to do this in green since it's the green step, and we're going to start at positive 60 kilojoules per mole. So I go over here and I'm like, all right, potential energies on this side of any potential energy graph, and our x-axis is always going to be time or reaction progress or something like that. So we're going to start at 60 because we are told in our problem to start there. Our delta H value up here says that over the course of that step, we lose 45 kilojoules per mole. So where I'm going to end that step over here, I want to be 45 less than 60. So 60 minus 45, that's what? 2015. So we're going to go over here and we're going to wait a little bit of time. The amount of time that you use on the x-axis is a little bit arbitrary because we are not told any time value, so you just want to move ahead in time. All right, so our E sub R over here, and this is our energy of our reactants, and this is our first set of intermediates. So I'm just going to label it intermediate right here. Now, once again, we're starting at E sub R, we're ending at intermediates for this step, but we have to pay attention to what we're told here to know how big to draw our hill. And since it says it's a fast step, our hill shouldn't be that tall. So again, we're not given a specific value for it, so I'm just going to make kind of a short hill. I'm going to go like this, and there's my step 1. All right. Now, let's look at step 2. I'm going to switch colors. Step 2 up here says that it is slow. Slow means my E sub A, or my hill, should be really tall or high, right? We are also told that the delta H value for this step is positive 65 kilojoules per mole. All right, so we are going to gain energy overall. So from 15, I'm going to add 65, right? And if you want to do that on a calculator, fine. If you want to do it in your head, fine. But ultimately, you want to end up all the way up here at positive 80 by the end of that step. Again, I'm going to move a little bit of an arbitrary amount of time, and I'm going to draw my hill pretty big. So make my hill up here, and we're going to come over to 80. And I'm going to label this intermediate 2. All right, we can see that the height of the hill here, real big. That's what we want. We can see we gained energy over time. That's good. Now I'm going to switch colors again. We're going to do step 3. Step 3 says it's a fast step as well, which means it shouldn't have a very tall hill. Again, we know that. And our delta H value here is negative 75. So that means that we should be an exothermic step and we should be losing energy over time. So 80 minus 75, and I know it's 80 minus 75 because we're up here at 80 for our intermediate 2. I'm going to go all the way down to 5 for the end of this reaction. And again, I'm not going to make my hill very tall because it's a fast step. And I'm going to go all the way down to my products. I'm going to label that E sub P. Okay? So this thing looks kind of wonky, right? But let's just do a quick guess and check. We know, based on our information, that our equilibrium step, our green step, it was fast, so it has a little hill, and we should have lost some energy. Both of those things are true. I see that I've lost energy from here to here in step 1. That's good. My second step was my slow step with a really tall hill, so I should have had a very tall hill and gain energy over time because it was endothermic with a positive delta H value. Great, I see that that has happened. And my last step was exothermic, and it was also a fast step, so I should have lost energy over time with a very small hill. Again, I can see that I lost energy and that my hill size is not that big. All right, so that's my sketch. Now, for some of the problems on your practice, you might be asked to label the intermediates as you go, in which case we wouldn't use labels like E sub R. Instead of E sub R, I would have literally just put my reactants there. So I could label that as 2NO. All right. In terms of my intermediates, I would not have put just intermediate 1. I would have listed N2O2 here instead of intermediate 1. All right, so those are a couple of different ways that you can sketch these graphs. And if you have problems trying to figure out, well, how do I space out my graph? Like how do I know what numbers go where? Please feel free to talk to me.